Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the vast theater of space, stars are not the stationary beacons of light we perceive from Earth. They journey through the cosmos, sometimes leaving their birthplaces entirely. Tonight, we explore a profound question at the intersection of astrophysics and galactic archaeology. Do stars retain information, chemical, orbital, or otherwise, about their original homes when they migrate between galaxies? Across the observable universe, stretching some 93 billion light-years in diameter, galaxies engage in slow-motion dances that occasionally bring them close enough for stellar exchange. Our own Milky Way galaxy, a barred spiral measuring 100,000 light-years across, is surrounded by evidence of these ancient encounters. The concept of stellar memory might seem abstract, but it underlies a revolutionary field called galactic archaeology. Just as archaeologists on Earth uncover human history through artifacts, astrophysicists examine stars as living fossils that preserve information about environments long since transformed or destroyed. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The stellar migration process occurs through several mechanisms. Tidal interactions between passing galaxies can strip stars from their outer regions. Complete galactic mergers incorporate entire stellar populations into newly formed structures. And sometimes, hypervelocity stars, accelerated to astonishing speeds by gravitational interactions, escape their home galaxies entirely, becoming intergalactic wanderers. The most dramatic evidence of stellar migration comes from our cosmic backyard. The Sagittarius dwarf spheroidal galaxy has been orbiting and gradually merging with the Milky Way for at least 4 billion years. Each close approach to our galaxy strips away stars from Sagittarius, creating stellar streams that now wrap around our galaxy like cosmic serpents. Using data from the European Space Agency's Gaia spacecraft, astronomers have identified approximately 30,000 stars in our solar neighborhood that originated in the Sagittarius dwarf. These stars now orbit alongside native Milky Way stars, raising the question, how can we distinguish these immigrants from locals born in our galaxy? The answer lies in stellar properties that function like genetic markers or passports. A star's chemical composition, its metallicity, reflects the elemental abundances present in its birthplace. Stars born in smaller galaxies like Sagittarius typically contain fewer heavy elements than native Milky Way stars. Their orbital characteristics also differ, as immigrant stars often travel on paths that don't align with our galaxy's typical rotation pattern. Perhaps most telling are certain chemical abundance ratios, particularly the proportions of elements, like magnesium, silicon, and calcium relative to iron, which vary between galaxies due to different histories of star formation and supernova events. These ratios create distinctive chemical signatures that persist throughout a star's lifetime, regardless of its travels. As our tools for astronomical analysis become increasingly sophisticated, we're beginning to read these stellar passports with greater precision, unraveling the complex migration patterns that have shaped our galactic neighborhood over billions of years. The stars above us, it seems, are not just lights in the darkness, but travelers with stories to tell, stories of distant homes and cosmic journeys spanning unimaginable distances. The concept that stars carry chemical signatures of their birthplaces represents one of modern astronomy's most powerful investigative tools. Every star forms from a cloud of gas and dust whose exact chemical composition reflects billions of years of previous stellar evolution in that particular region of space. This composition becomes frozen into the star at birth, creating what astronomers call its chemical fingerprint, a distinctive pattern that remains largely unchanged throughout the star's lifetime. Spectroscopy provides the key to reading these chemical fingerprints. When starlight passes through a prism or diffraction grating, it separates into a rainbow-like spectrum crossed by dark absorption lines. Each line represents a specific element absorbing light at characteristic wavelengths, allowing astronomers to determine precisely what elements exist in a star's atmosphere and in what proportions. The European Southern Observatory's very large telescope in Chile hosts an instrument called FLAMES, Fiber Large Array Multi-Element Spectrograph, that can simultaneously analyze the chemical compositions of up to 130 stars with remarkable precision. Similar instruments on the Sloan Digital Sky Survey telescopes have collectively gathered spectra for millions of stars, creating vast libraries of stellar chemical signatures. What makes these signatures so valuable for tracing stellar origins? Stars born in dwarf galaxies typically show lower overall metallicity, a measure of elements heavier than hydrogen and helium, than those born in massive galaxies like the Milky Way. But the real diagnostic power comes from examining specific element ratios. The ratio of alpha elements, including oxygen, magnesium, silicon, calcium, and titanium to iron, provides particularly valuable information about a star's birthplace. These elements form primarily in different types of supernovae. Alpha elements come predominantly from type 2 supernovae, the explosive deaths of massive stars, while iron comes largely from type Ia supernovae, thermonuclear explosions of white dwarf stars in binary systems. Since massive stars evolve and explode quickly, while white dwarfs require longer to develop, the alpha-to-iron ratio in interstellar gas evolves over time, in a pattern that depends on a galaxy's star formation. History. Dwarf galaxies, with their typically sporadic star formation, develop chemical evolution tracks distinct from larger galaxies with more continuous star formation. The telescope Apogee, Apache Point Observatory Galactic Evolution Experiment, has measured detailed chemical compositions for more than 100,000 stars in the Milky Way, revealing populations with alpha element patterns that don't match our galaxy's typical chemical evolution. Many of these chemically distinct stars follow orbits suggesting they originated in now consumed dwarf galaxies. Beyond overall metallicity and alpha element patterns, astronomers also examine abundances of rare elements produced through specific nuclear processes. Elements formed through the rapid neutron capture process, R process, like europium, often show distinctive abundance patterns in dwarf galaxies compared to larger systems. The star HD 186-755 offers a compelling example of chemical memory preserving stellar origins. Located just 870 light-years from Earth, its extreme R process enhancement and unusual elemental abundance pattern identifies it as a likely immigrant from a disrupted dwarf galaxy, despite now orbiting within our galaxy's disk. Perhaps, most remarkably, certain ultra-faint dwarf galaxies contain stars with such distinctive chemical patterns that astronomers can identify their siblings scattered throughout the Milky Way. The distinctive chemical signatures of stars from the Gaia Enceladus dwarf galaxy, consumed by the Milky Way 8 to 10 billion years ago, have allowed astronomers to identify thousands of its former members now dispersed throughout our galaxy's halo. While a star's chemistry preserves a snapshot of its birthplace, its orbital path through space functions as a dynamic record of its journey. Stars don't simply forget their origins when they change galaxies. They carry orbital memories that persist for billions of years, albeit gradually altered by gravitational interactions. When a dwarf galaxy merges with the Milky Way, its stars initially maintain coherent motion, traveling together along similar paths. Over time, this coherence gradually disperses, but subtle correlations in velocity and direction remain detectable long after the original structure has dissolved. These correlated motions function like cosmic fossils, preserving evidence of ancient galactic structures that no longer exist in their original form. The European Space Agency's Gaia spacecraft, launched in 2013, has revolutionized our ability to read these orbital histories. By precisely measuring the positions, distances, and motions of nearly 2 billion stars, Gaia has created what astronomers call a six-dimensional map of our galaxy, recording not just where stars are located in three-dimensional space, but also how they're moving in all three dimensions. This unprecedented data set revealed something remarkable. The Milky Way's halo, the spherical region surrounding the galaxy's disk, contains distinct streams and overdensities of stars that move together in coordinated patterns. These structures represent the remnants of dwarf galaxies, torn apart by the Milky Way's gravitational field, their members now spreading out along the original orbit of their parent galaxy. The Helmi stream illustrates this phenomenon beautifully. Discovered in 1999 and studied in much greater detail with Gaia data, this collection of several hundred stars follows similar orbital paths through the Milky Way's halo. Their coordinated motion reveals them as remnants of a dwarf galaxy that merged with the Milky Way approximately 8 billion years ago. Though physically dispersed across thousands of light years, these stars continue to trace the ghost of their original galaxy's orbit. Even more dramatic is the Gaia Enceladus structure, sometimes called the Gaia sausage, due to its elongated appearance in velocity space. This massive collection of stars, potentially numbering in the hundreds of millions, represents the remains of a galaxy approximately the size of the small Magellanic Cloud that collided with the Milky Way 8 to 10 billion years ago. Though thoroughly mixed with the Milky Way physically, these stars follow distinctive, highly elongated orbits that preserve the memory of their dramatic entrance into our galaxy. Stellar orbits also preserve information about less dramatic migration processes. The phenomenon of radial migration allows stars born in one part of a galaxy's disk to move inward or outward while maintaining nearly circular orbits. Analysis of our Sun's orbit and chemical composition suggests it may have formed about 2,000 light-years closer to the galactic center than its current location, gradually migrating outward over its 4.6 billion-year history. Perhaps most intriguing are stars with orbits so energetic they appear to be just passing through the Milky Way. Hypervelocity stars travel at speeds exceeding the galaxy's escape velocity, typically over 500 kilometers per second. Some originate from the violent disruption of binary star systems by the supermassive black hole at the galaxy's center. Others appear to have extragalactic origins, perhaps ejected from the large Magellanic Cloud or other nearby galaxies. Above and around the familiar spiral disk of the Milky Way extends a vast, nearly spherical halo populated by ancient stars and star clusters. Once thought to be a relatively featureless distribution of old stars, modern observation techniques have revealed this region to be crisscrossed by numerous stellar streams, ribbon-like structures containing thousands or even millions of stars moving in coordinated patterns through space. These stellar streams represent one of the most visible and compelling forms of stellar memory. Each stream consists of stars that once belonged to a satellite dwarf galaxy or globular cluster that ventured too close to the Milky Way. Our galaxy's powerful gravitational field produced tidal forces, similar to how the moon raises tides, on Earth but far more destructive, that stretched and ultimately dismembered these smaller stellar systems. The physics behind stream formation follows a predictable pattern. As a satellite galaxy orbits the Milky Way, stars closest to our galaxy feel a stronger gravitational pull than stars on the far side. This differential force stretches the smaller galaxy along its orbit. Eventually, some stars escape through gravitational gateways called Lagrange points, forming leading and trailing streams that continue along roughly the same orbital path as their parent satellite. The Sagittarius stream provides the most spectacular example of this process in action. Discovered in 2001, this structure consists of stars stripped from the Sagittarius dwarf spheroidal galaxy over approximately 4 billion years of orbital interaction with the Milky Way. The stream forms a complete polar ring around our galaxy, spanning the entire sky and containing hundreds of millions of stars. Computer simulations of the Sagittarius stream suggest the parent dwarf galaxy has completed at least 3 full orbits around the Milky Way, leaving behind successive layers of stripped stars with each passage. By studying variations in stellar densities and velocities along the stream, astronomers can reconstruct this orbital history with remarkable precision. The discovery of additional streams accelerated dramatically with the release of Gaia satellite data. Astronomers have now identified more than 60 distinct stellar streams in the Milky Way's halo, Each preserves information about both its progenitor and our galaxy's gravitational field. The GD1 stream, spanning approximately 30,000 light-years, likely originated from a globular cluster that was completely disrupted approximately 2 billion years ago. The orphan stream, named because astronomers initially couldn't identify its progenitor, spans nearly half the northern sky. Recent evidence suggests it may originate from a dwarf galaxy currently hidden behind the galactic disk. These streams function as sensitive probes of the Milky Way's dark matter distribution. Any deviation from a perfectly smooth gravitational field, perhaps caused by concentrated clumps of dark matter or the gravitational influence of small satellite galaxies, would create corresponding disturbances in stream structures. Astronomers have detected several such perturbations in the GD1 stream, potentially indicating encounters with dark matter substructures. Stellar streams also serve as chronometers. The degree of dispersal along a stream, how much it has stretched and spread, correlates with its age. Newly formed streams remain relatively narrow and well-defined, while ancient streams become progressively more diffuse as their stars gradually disperse due to various gravitational interactions. Most remarkably, streams preserve information about galaxies that no longer exist in their original form. The Phoenix stream, discovered in 2016, appears to originate from a type of ancient globular cluster that theory suggests should have completely dissolved billions of years ago. Yet its distinctive stellar populations and chemical composition preserve the memory of this otherwise extinct stellar system. The space between galaxies, the intergalactic medium, is not entirely empty. Scattered through these vast cosmic voids are stars that have completely escaped their birth galaxies, becoming true wanderers in intergalactic space. These stellar nomads represent the most extreme examples of stellar migration and raise fascinating questions about how much of their original galactic heritage they preserve. The primary mechanism creating intergalactic stars involves galactic interactions and mergers. When galaxies collide or pass near each other, their gravitational interactions can eject stars at velocities sufficient to escape both systems entirely. Computer simulations suggest between 10 and 20% of a galaxy's stars might be ejected during major merger events. Observations with the Hubble Space Telescope and large ground-based telescopes have detected a diffuse glow between galaxies in dense galaxy clusters, a phenomenon called intra-cluster light. This faint luminosity comes from billions of stars floating freely in intergalactic space, unbound from any particular galaxy. In rich clusters like Virgo and Coma, intracluster stars may constitute up to 15% of the cluster's total stellar mass. Individual intergalactic stars prove challenging to detect due to their extreme distances and isolation. Astronomers have identified candidates through two main approaches. Supernovae occasionally reveal otherwise invisible intergalactic stars when these stars explode, briefly outshining entire galaxies. Additionally, gravitational microlensing, where a passing star briefly magnifies light from a more distant source, has identified potential intergalactic stars in several galaxy clusters. Beyond these ejected stars, astronomers have identified a second, more exotic category of intergalactic travelers, hypervelocity stars. These rare objects travel at speeds exceeding 1,000 kilometers per second, fast enough not only to escape their birth galaxies, but potentially to traverse intergalactic space. Several mechanisms can create hypervelocity stars. The most energetic involves close encounters with supermassive black holes. When a binary star system passes near such a black hole, one star might be captured, while the other receives an enormous gravitational slingshot effect, accelerating to speeds exceeding 1,000 kilometers per second. Other hypervelocity stars originate from supernovae in binary systems, where the explosion provides sufficient asymmetric force to eject the companion star at extreme velocities. The star US 708, discovered in 2005, represents one of the most famous hypervelocity stars. Traveling at approximately 400 kilometers per second, relative to the Milky Way's rotation, its trajectory traces back to the galactic center, suggesting an origin involving our galaxy's central supermassive black hole. More recent discoveries include stars traveling fast enough to escape not just the Milky Way, but potentially the entire local group of galaxies. Intergalactic stars experience environments radically different from their stellar siblings that remain within galaxies. The intergalactic medium contains extremely low gas densities, typically less than 1 atom per cubic meter, and minimal dust. Without this material to interact with, intergalactic stars and their potential planetary systems remain largely unaffected by their environments over billions of years, potentially preserving primordial conditions from their formation. This isolation makes intergalactic stars particularly valuable for understanding galactic evolution. Their chemical compositions represent unaltered snapshots of conditions in their birth galaxies at specific moments in cosmic history. By studying the compositions of intergalactic stars with different ejection ages, astronomers can potentially reconstruct chemical evolution timelines for their original galaxies. Future telescopes like NASA's Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will dramatically improve our ability to study these cosmic castaways, providing unprecedented insights into both their properties and the galactic interactions that launched them on their intergalactic journeys. Our home galaxy, the Milky Way, contains approximately 200 billion stars. While most were born within our galaxy's borders, a surprisingly large fraction, between 20 and 30%, originated elsewhere. These stellar immigrants have become so thoroughly integrated into our galaxy that identifying them requires sophisticated astronomical detective work, combining chemical, dynamical, and age-based evidence. The most substantial contribution of immigrant stars comes from a single event, the Gaia-Enceladus merger. Approximately 10 billion years ago, a dwarf galaxy roughly 1/4 the mass of the Milky Way collided with our galaxy. This cataclysmic event delivered several 100 million stars into what would become the inner halo of the Milky Way and potentially triggered the formation of our galaxy's thick disk component. Astronomers identified this ancient merger by combining Gaia satellite data with chemical analysis from ground-based spectroscopic surveys. Stars from Gaia-Enceladus follow distinctive orbital paths with high eccentricity, meaning their orbits deviate significantly from perfect circles and show chemical compositions consistent with formation in a smaller galaxy with lower overall metallicity than the Milky Way. Beyond Gaia-Enceladus, astronomers have identified at least 5 other significant merger events contributing immigrant stars to our galaxy. The Sequoia and Tamnos events represent additional ancient mergers that deposited stars primarily into the outer regions of the Milky Way's halo. More recently, the ongoing incorporation of the Sagittarius dwarf galaxy has added approximately 100 million stars over the past 3 billion years. These immigrant stars don't remain confined to the galactic halo. Simulations show that over billions of years, gravitational interactions gradually alter stellar orbits through a process called phase mixing. This process brings some immigrant stars into the Milky Way's disk, where they can potentially orbit near the Sun. The chemical signatures of these immigrant stars create patterns astronomers call chemodynamical substructures, groups of stars sharing both similar chemical compositions and orbital characteristics. A survey called HERMES, High Efficiency and Resolution Multi-Element Spectrograph, at the Anglo-Australian Telescope has identified numerous such substructures in the solar neighborhood, revealing the rich merger history preserved in nearby stars. Determining exactly which stars around us originated elsewhere involves combining multiple lines of evidence. Chemical composition provides the foundational clues, particularly abundance patterns of elements like magnesium, silicon, calcium, and titanium relative to iron. Orbital dynamics add another layer of information, with stars on highly inclined or eccentric orbits more likely to have extragalactic origins. Finally, age determinations help establish chronologies for different merger events. Perhaps most surprising has been the discovery of immigrant stars in unexpected locations. Traditional models suggested merged dwarf galaxies would contribute stars primarily to the Milky Way's halo. However, recent studies have identified likely extragalactic stars within our galaxy's thin disk, the relatively flat component where the Sun resides. These stars have gradually settled into disk-like orbits through gravitational interactions over billions of years, while retaining their distinctive chemical signatures. Some immigrant stars don't come from mergers at all, but represent individual stellar captures. The hypervelocity star HE 199-418, traveling in the direction opposite to the Milky Way's rotation at nearly 300 kilometers per second, appears to have originated in the Large Magellanic Cloud before being gravitationally captured by our galaxy. Even our Sun isn't immune from migration questions. While most evidence suggests it formed within the Milky Way, its location relatively far from the galactic center, and its somewhat unusual chemical composition have led some astronomers to speculate about potential extragalactic origins. Current consensus favors a native Milky Way origin, but with significant radial migration outward from its birthplace. The emerging field of galactic archaeology, reconstructing galaxy formation histories by excavating the chemical and dynamical properties of their stars, stands at the threshold of a revolutionary period. Just as traditional archaeology pieces together human history from artifacts and remains, galactic archaeologists reconstruct cosmic history by reading the memories encoded in stellar properties. Current efforts focus on the Milky Way simply because it's the only galaxy where we can observe individual stars in sufficient detail. The Gaia space mission, launched in 2013, has measured positions and motions for nearly 2 billion stars, approximately 1% of our galaxy's total stellar population. When combined with ground-based spectroscopic surveys like APOG, Gaia, and the Sloan Digital Sky Survey, these data reveal the Milky Way's complex assembly history with unprecedented clarity. What emerges is a picture of galaxy formation far more dynamic than previously imagined. Rather than forming in isolation, galaxies like the Milky Way grow substantially through mergers and accretion events. Each event leaves behind stellar populations, with distinctive chemical and orbital signatures, memories of their origins that persist for billions of years. This realization has profound implications for understanding galaxy evolution throughout the universe. If the Milky Way's history involves such complex interactions, similar processes must shape the hundreds of billions of galaxies beyond our own. The stellar memory phenomenon becomes a universal tool for decoding galactic histories. The next generation of astronomical instruments promises to extend galactic archaeology beyond the Milky Way. The James Webb Space Telescope, successfully launched in 2021, can resolve individual bright stars in nearby galaxies like Andromeda. The Nancy Grace Roman Space Telescope, planned for launch in the mid-2020s, will push these capabilities further, potentially identifying stellar populations from ancient merger events in dozens of nearby galaxies. Ground-based, extremely large telescopes currently under construction, including the 30-meter telescope, Giant Magellan Telescope, and European Extremely Large Telescope, will provide unprecedented spectroscopic capabilities. These instruments will measure chemical compositions for stars throughout the local group of galaxies, allowing comparative galactic archaeology across multiple galactic systems. Beyond observational advances, computational models continue to refine our understanding of how stellar memories persist and transform. The FIRE, feedback in realistic environments, simulation project combines cosmological models with detailed physics of gas dynamics, star formation, and stellar feedback to trace how stars move through evolving galaxies. These simulations confirm that stellar chemical signatures remain reliable origin indicators even after billions of years of orbital evolution. The eventual convergence of advanced observations and sophisticated models promises answers to fundamental questions about galaxy formation. How common are major merger events versus more gradual accretion? What fraction of stars in typical galaxies originated elsewhere? How do the chemical evolution histories of different galaxy types compare? The answers emerge as astronomers continue decoding the memories preserved in stellar populations. Perhaps most profound is how stellar memory connects to cosmic evolution more broadly. Stars represent living artifacts that preserve conditions from throughout the universe's history. The oldest stars in the Milky Way's halo formed more than 13 billion years ago, when the universe was less than 5% of its current age. Their chemical compositions preserve information about the earliest generations of stars, mysterious objects that formed from pristine gas containing only hydrogen, helium, and trace amounts of lithium produced during the Big Bang. By reading stellar memoirs, astronomers trace not just the histories of individual galaxies, but the broader narrative of how matter organizes itself into increasingly complex structures across cosmic time. From the smooth distribution of matter in the early universe to the rich galactic ecosystems we observe today, stellar memory provides the evidential foundation for reconstructing this cosmic evolution. Do stars remember the galaxies they came from? The evidence overwhelmingly confirms they do. Through chemical fingerprints, orbital dynamics, population patterns, and other properties, stars preserve information about their origins across billions of years and millions of light years. As we continue developing more sophisticated tools for reading these stellar memories, the complex history of our cosmic neighborhood comes into increasingly sharp focus, star by star, galaxy by galaxy, revealing the magnificent dynamic story of our evolving universe.